Okay, so I've got my little pointer. Yeah, that's how it works. Good. Okay, I want to talk to you about test limits. You guys produce some amazing code, use amazing equipment, and you're testing lots of product. But when I go and audit companies and I go and look at their testing, people are very, very happy to show me how many things are passing. Oh, look at this. Pass, 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 pass. First pass yield is 98%, 99%. I'm absolutely not impressed. Why? Because I don't believe it until I see it. I want to go in and look at the data and see how good the testing actually is. Are the methods good? And in particular, what do the test limits look like? So what I want to do today is just briefly, 45 minutes, so we've got almost no time, just show you what a cost and quality advantage you can have from having good test limits. And when I say robust, what do you think I mean by robust test limits? Oh, by the way, the people who give the best questions, answers, I promise I'll do something for you. I'll crunch a whole bunch of data for you and give you some beautiful reports that may be very eye-opening. Okay, so what do you think I mean by robust? Come on, it's in the dictionary. Go for it.
All right, well, I've had problems where, for instance, a ZDO regulating your power supply, and you gradually, yeah, that's limits. And then you realise that they picked out all the 1% in the middle, and it's actually double up. You put these limits in that, next batch failure.
Yeah, I mean, that's an interest. Yeah, bimodal data is, by the way, I like statistics. I've got a statistics joke for you if you like. But yeah, bimodal data. But that's not really what I'm after. I want robust testing and robust limits such that my customers get absolutely what we sell. They don't get manufacturing defects. They don't get junk. Robust for the customer. And that ensures that we have no field returns, no recalls, and that's good for the bottom line of the company. So, robust for me is not that it can pass regardless of what's going on. It's that it is very, very good at not passing unless it really is good. Okay. Oh, and if you want to look and see who I am or what I do, look on LinkedIn. Okay, so who develops tests and creates limits here? Anyone? Anyone doesn't? So where do those limits come from? And I want some answers. Where do you get your test limits from? Just one at a time. Somebody? Design engineering. Okay, and where do they get it from? Okay, it was interesting yesterday, the chat GPT. Oh, you know, we're going to dump a datasheet into, you know, an AI bot, and it goes and generates something. How good do you think those test limits are going to be coming from a datasheet in the real world for detecting outliers and crappy product? And I bet there's a whole bunch of you here that'll say, yeah, that'd be perfect, be fantastic. No. Once you get to understand data and normality and what you're naturally building, you'll know that test limits are something very, very special. And it's something that I feel most people don't really address. I do lots of auditing of companies. ResMed, we buy lots of companies. You know, we've got a competitor, they're making something, you know, we want that market. So we just go and buy the company. Buy it, grab their technology, pretty much shut down their company, throw away their product, take some patents, but now we own their customers. And that's kind of cool. The interesting thing for me is they throw me on a plane, send me over somewhere, and I get to look at all their data, all their gory details. And it's staggering how shitty some of the testing that goes on out in the real world in medical device companies. And I've worked medical, military, aerospace all my life, and it can be quite depressing how bad people are at creating test limits. Okay, so I've rubbed your noses in that, right? You understand where I'm coming from. Okay, so now here's where I go a bit old school, okay, where it's a bit ancient. Look at this, Excel. Okay, what I do is I go to companies, anybody, you give me some data and I'll be able to produce some stuff that we can grade and look at very, very quickly without making any fancy things, without anything at all. I can just crunch some numbers. And what you can see here is some test names, and this is coming from in-circuit tests. There's some, discrete components, but there's also some functional tests like rails, 3.3 volts. And I've got a few things here, number of samples, outliers. Oh, that's an interesting one. How many outliers are there? And this is these two numbers are both 0 is perfection, and there's no top end. You get billions. How do I create them? What do they mean? Well, big numbers, bad. 0, good. Okay, and they're coloured sort of accordingly. And here, this is sorted by score. Over here, what's up? This one says, your upper limit looks like it needs a bit of attention. But these ones, no comments. They look kind of good. Over here, we've got histograms. The histogram we're looking at there, it's kind of funky. Has anyone seen histograms like this before? It comes from the 1980s. We used to use histograms like this because it was easy to print. But the good thing is you can have a sheet, like an Excel sheet with thousands of these things, and you can immediately look down them and just say, yeah, I know what they look like. It doesn't take much brain power. Now you're going to say, well, what does it mean? Well, a dash is a 0, 1 is 1, 2 is 2, 9 is 9, lowercase a is 10 occurrences. Lowercase b is 11. Lowercase z is 35 occurrences. Uppercase a is 36. Uppercase z 61. And the hash symbol says 62 or more. Now, it's bloody simple. It's 7-bit ASCII stuff. It's remarkably simple to make. And we can see here, all this data, basically it's sitting within its limits. And, there's some test data. This data actually looks pretty good. Oh, I also put in CPK. And I've heard people mentioning CPK, and yeah, I don't pay much credit to CPK. It's pretty much meaningless to me. Now, I know I've argued with test manager or at Cochlear about CPK, but he and I just lock horns on it. Anyway, so that's what I do. And I can go away and I can filter things and look and see which tests are crap, which tests are good, which ones need addressing, and whatever. Very, very fast. Now, I'm only showing you the good stuff here, but we have some bad stuff too. You can see these scores. They're rocketing up. Some have got lots of outliers. Outliers means that there's some data on the bottom or top 20%. Ideally, you want the middle 60%. And if you're American, like one of my American colleagues, he says, oh, the bottom fifth, the middle 3/5 and the top fifth. And it's like, God, why do you guys do that? Use fractions all the time. They love it. And so this gives me a really quick way of reconciling which tests have got something a bit screwed up in them. It's pretty apparent to me that this test here is, it's going to be failing on the low side very often. So it's going to be a problem to manufacturing. They're probably going to have lots of failures at that point. You really need to fix this damn test up. You know, it's got upper and lower limit problems. It's really problematic. And it's also bimodal, like was mentioned. Here's an interesting one. You guys are really geeky. Look at that data. It's in little clumps across there. Who knows why? Absolutely. Who said that? Beautiful. Well done. It's the ADC. It's on too high a range. The ADC's quantizing out. And so maybe that you should go to a lower range. Little things like that you can see. Okay, so this is a tool I use. And there's two types of errors in statistics. This is called a type 1 error. It means you're going to have false fails. And what does that mean? Well, they're not so good for EMS, people who manufacture things, because you're failing things wrong. You shouldn't be failing it. What does it mean? It means you're probably going to have rework that you shouldn't have. It means that production is going to slow down. You're going to have too much retest. All these nasty things happen. But your customers are pretty safe, other than all the excess rework that they're going to do. The other kind of error that we've got here, this is called a type 2 error. And if you're going to search for this, you know, wiki it, it's type, do underscore, and then Roman numerals, type I, type II. Type 2 errors are insidious. They're the kinds of errors where you really couldn't fail. It's hard to fail. You're going to ship possibly crappy product. Now, they're the kind of products that are going to fail in the field, be problematic to you. You may even have to have a recall because of it. Type 2 errors are bad for the OEM and the customer, great for the EMS. Type 1 errors, bad for the EMS and not pretty inert to the OEM and the customer, because you generally don't get to see them unless the rework is excessive. Okay. Now, that Excel spreadsheet links over to some beautiful 7-bit ASCII. This is stuff that, by the way, this is the way I used to show it on VT100 terminals in 1980. So, is anyone not born in 1980? A few of you. Anyway, this is what I used to do in 1980. And look, if you see something in here and you want to investigate, there's an adjoining file that basically gives you all this kind of nice, tasty data, number of samples, outliers, the score, CPK, and what's wrong. And you'll notice that's the CSV format. That's how it gets into the Excel. The mean value is not displayed, median, bin width of the histograms, standard deviation. The tool also tells you whether it's a normal distribution or not. If it's bimodal or it's trimodal or whatever, anything crazy like that, this thing will come up and say, hey, that data's not normal, don't trust standard deviations. And it tells you, lower limit, upper limit, tells you how many standard deviations they are away. The lowest measured value, highest measured value, how many standard deviations they are away. And if it's not so good, it tells you, why don't you try this? 12.069, 2%. Or lower limit that, upper limit this. And that will fix this problem. This is what I deploy to my contractors. Now, the interesting thing about ResMed is we make printed circuit boards. We make a lot. We make these kind of things, 1,000 odd components, 0201, very, very small micro BGAs, that kind of stuff. Close enough to 50,000 boards a day. Okay, so that's a few. Our scrap rate is about 0 a year. We don't really scrap anything unless it's been dropped on the floor, it's got mechanical damage. The people that repair our boards, they might know Ohm's law, maybe. We don't tell them how the board works. We design our products such that they're inherently testable. And yeah, so we're pretty good at doing that. Okay, so can anyone see something on that page? And I put that page on there on purpose just to stimulate some conversation. Chris?
The one on the right.
Yeah, that guy. This comes from system spec. The limits here, 2.1 and 3.1, were a system spec with this company we bought. And when I saw this, I inquired to the test manager and said, why is this test so terrible? And look at this outlier here in this sample of 20,000 that you just gave us. Is that a good unit? And he said, yeah, it passed the spec. I then asked him the question. It's a medical device. You want to buy one of our medical devices, I'll sell you one. And it's going to have that test in it. It's that unit. Do you want it? He's like, no way. Forget it. I don't want that one. I want one of these guys. It's over here. I said, well, why did you pass it? Why did you accept it if it's... And by the way, how many standard deviations is that? 100. 100 standard deviations away from the mean. And he passed it. And when you ask him, where did you get those limits from? He said it came from the system spec. And sure enough, it did. I went and checked. Thankfully, someone's put a schematic up, right? Is everyone happy about that? And unfortunately, it's a bit small, but anyway, here's the histogram plotted a slightly different way. There's that data point there. It just so happens that it's the motor drive, the phases, they're either 24 volts, 12 or 0, okay? And this goes back into an ADC that reads what the phase of the motor is to know how to spin the motor. The motor doesn't have any encoding on it. It's a back EMF sensing motor. And this one unit here, when you look at it, it actually resolves down to one of the channels, and when you look at it, it's one of these BAT54 Schottky diodes is leaky. Well, I must admit, the test for the BAT54 also showed that there was a real problem, but they also had super wide limits for that. Why? Because they kept finding dodgy parts and kept widening the limits. Now, one of my findings with this company was that you guys aren't really in control. This is really shitty. This is bad. And we've got to fix this. So, and I kind of pointed out, listen, you know, it's this guy here. It's dragging up to 3B3, and that's where the bias is coming in. And it was pretty simple. We dragged out that serial number. It hadn't been shipped. Pulled it out, put a multimeter on it, sure enough, leaky as. And the guy was, he wasn't embarrassed at all. He said, look, it's a system spec. I'm just using system specs, mate. That's what I do. I don't have any freedom to change system specs. Well, that's where I come in and say, forget that. I don't care what the developer says. I don't care what the data sheet says. I only want to ship normal product. And so I've got a mechanism that, you know, you can choose to use or not. Start with wide limits when you're doing NPI, when you're doing prototyping. Learn what you've got and then bring it in, and then only increase the limit that is necessary to move as you find variation in the batches, and you will. And just to give you an idea of how much variation that little dot is inside this system spec, Robert Wadlow He's pretty tall, isn't he? Does he look tall? Well, have a guess how many standard deviations he is. This bloke here, he's 1.8 metres tall. Robert's 2.72 metres. Sorry for anyone who uses imperial measures. He's 15 standard deviations bigger than a standard male, okay? 15, not much. That thing is 100 standard deviations. So Robert would be about here somewhere. That would be where he would appear as a data point if it was on that graph. Pretty easy to overlook. And yet, you can see that that's a big difference. I have trouble trying to explain to QA people and developers and engineers and all kinds of people exactly what it means when something is big like that. Visualizing standard deviations is a very hard thing for people to do. But if you think about it this way, and if you show and say, look, he's only 15, we're talking 100. That's 8 metres tall. He wouldn't fit in this roof. He's a big guy. So, question is, what do you do about it? Well, from my perspective, if I'm going to buy a product off any of you folk, I would like to know that the unit that I am buying is normal. It's homogeneous. It's the same as every other one. You could not differentiate it. That's what I would like. And unfortunately, with all of the companies that I've audited so far, that's not what you're getting. How many people have had TVs that stop working, microwaves that don't work, all that kind of crap? It could be that it's just shitty testing that's going on. And methods are one thing, limits are something else altogether. Who controls your test limits? And so let's just find out. Who controls your test limits? Now, Cochlear, I know how you guys do it because I interact with those guys a bit. Who else modifies test limits here? No one. Come on. You're having me on. Yeah. How do you do it?
I think probably do a bit of a combination approach. What it should be, what I'm getting in the batch, and do some and sort of find limits that I'm comfortable with that shouldn't cause. But as you say, you want your limits tight, so you can find those horrible outliers. But you don't want them too tight that they're a pain in the ass to the CM, and they start, I've had CM a limit too tight before, and the CM was touching a Zetadog with a hot iron, running through the tester quickly, while it's still warm, no cuts.
Yeah, yeah, good. Yeah. Well, it's definitely something that I see is a bit of a problem. By the way, I told you that with a typical board, something like this, we'll do about 2,500 analog measurements. 2,500 takes about 60 seconds. That includes flashing and testing and turning on power and measuring all that kind of stuff, doing lots of digital testing. The way that I do statistics, we had a statistician that joined ResMed years ago. Butte guy, lovely. He and I got along like a house on fire. He said to me when he found out that I was doing lots of statistics, he said, oh, right, and you're using Minitab, aren't you? And I said, no, don't use Minitab. He said, oh, we've got to. Medical company, FDA wants us to use Minitab. We've got to. Cochlear, you use Minitab, don't you? Yeah, there you go. And so I said to the statistician, hey, well, listen, okay, I've got some data for you. And I gave him a USB stick with 1,000 boards on it with 2,500 analog tests in it. And he opened it up and he said, which test are we looking at? And I said, we're looking at all. And he said 2,500 objects that, he said, this is going to take 3 months. He said, it makes 2 A4 pages of data and things to look at. And I said, no, I want it like in 10 minutes and I just want to see what's the worst tests. He said, no, Minitab doesn't do that. And I've spoken to Minitab and MATLAB and people like that, and they just don't do it. They said, no, forget it. You're on your own. So Python to the rescue. So your customers want reliability, and reliability and the ability for you not to get field returns, I think is very important. The fact that, I mean, most everyone here deals in functional testing. If you had the next layer of testing beyond functional, could you imagine if you didn't actually find faults that you could find because your limits were just crap? It'd be terrible. You really want the next person, and for most people here, I think the customer is the next person who gets the gear. Is that right? Maybe, yes, no, sometimes. So you really want to keep your customers free of this kind of idiocy. And even with simple things like voltage regulators, you really have to look at the data. There's the 3.3 volt analog on that board there. It's a 1.8% regulator, but it always regulates about an order of magnitude better than that. So do you want to find it when it's nearly an order of magnitude worse than all the others in the batch? And I say, yes, I do. And I don't mind failing a few units that just look oddball. And that's been the success of ResMed over the years, being able to vet unusual product. Yeah, the suppliers, unfortunately, they want to ship and they're constantly blowing limits out unless you've got good controls on them. In medical, we're pretty good at being able to control the suppliers. Outliers to me are not acceptable. If they are acceptable to you, think about it. Are they really? Do you want to receive something which is oddball, that's very, very different to everything else that you're making? And I would suspect you wouldn't. So test limits matter. I hope I've stimulated a few people to think about their test limits, not just testing and not just making stuff that does pass. Because, yeah, you can't really get me convinced that that's excellence. So I'm going to make you an offer. Yeah, you take the blue pill, the story ends. You just go back and do whatever you used to do before. You write the limits, you change the limits, and you just let it happen. But you take the red pill, you listen to what I say, examine your testing, examine your limits, examine your methods, and we go down the rabbit hole, and it's deep, and it's problematic, but the benefit is it's a cost quality benefit that you will get at the end of the day. I guarantee it. 20 years, 25 years at ResMed doing this, and we're a clear indicator. We're way better than world class. Our defect rate is running at a stupendously low figure. It's remarkable. It's a glowing attribute for pursuing this method. Anyway, and anyone who's more interested with this kind of thing, you can contact me and ask more. Okay.